Hi everyone. So today we're going to learn about Newton's law of gravitation. It's going to be a very short video because there's very little here that you need to learn. The problem is always really being careful with what your symbols mean and knowing how that corresponds to a centripetal force and all that stuff. Okay. So what basically Newton discovered was that two masses attract each other, and that the more mass they have, the greater the attraction between them. And you probably know this already. Now, this means, for example, that two people attract each other gravitationally. It's just that the gravitational force is just so weak that you need a huge amount of mass to actually feel anything. So really you need a body the size of the Earth to really feel an appreciable force. But yes, there is a gravitational attraction between any two bodies that have mass. Now, of course, the more mass you have, the more force that you feel. And there's another thing that is important, which is also the distances between the bodies. Because, for example, we feel the attraction of the Earth very strongly, but we don't feel the attraction of the Sun very strongly, even though the Sun is way, way, way bigger. And the reason for that is simply that the Sun is very far away from us, so that the gravitational field that it exerts on us is very weak compared to that of the Earth, which is much closer. Now, we can turn this understanding into an actual formula, and most of it you can just figure out as you go. So the idea is that we want to find the force between two bodies, and we know that it's going to depend on three things: the mass of the body, the first body, the mass of the second body. Now, normally we take one of the bodies to be smaller than the other one, but we don't have to. We normally do this because otherwise there's subtleties involving where we measure things from. And then the last thing that we care about is the distance between the centers of the two bodies, and we call this distance r. Now, a lot of the people are tempted to say that this is a radius, but it is not a radius. A radius is the distance between the center of a sphere and its side. This is not the distance between a center of a sphere and its side. This is the distance between two centers of two spheres. So really this r means the distance between the centers of the bodies. Now, for all of this, we're going to assume spherical bodies. The law does not hold up if the body is not spherical. However, if the body is spherical, we can assume that all of its mass, it acts as if all of its mass was located in the middle. So again, spherical bodies, and this r corresponds to the distance between the centers, not the radius. When we talk about the radius, we use the letter big R. Okay. So anyway, we know that the force depends on these two masses, and we know that the bigger these two masses are, the bigger the force will be. So it just stands to reason that these two things are multiplying. We also know that the bigger this distance is, the smaller the force is. So again, it stands to reason that these things should be dividing. Now, what's not so clear is that there should be a squared here, but there is a square here. And the reason for this is that the force spreads out over a larger and larger area. And as you know, the area of a sphere is equal to 4 pi r squared. So really we're saying that the force is spreading out over a bigger and bigger sphere. Therefore, it gets more and more diluted, not with r, but with r squared. And finally, this is in newtons, which are human units, and this is in kilograms and meters, which are also human units. So we need some sort of constant to change between nature's units and ours. And for that we use G, which is Newton's constant. Now, Newton's constant is very, very, very small. So small, that it's almost impossible to feel the gravitational attraction between any two regular bodies, and you need, massive, really massive stuff to feel it. So the value of G is 6.67 times 10 to the minus 11. And now the units, we want to get newtons, so I'll start with newtons. And now we need to get rid of, kilograms squared, so that needs to be dividing. And now we also need to get rid of meter squareds, which are dividing, so that needs to be multiplying. So it's Newton meter squared over kilogram squared. And this is Newton's law of gravitation. Okay, that's pretty much it. Now, this is really all you need to know, and the rest just follows. And I am going to ask you to derive the rest. So if you want to stop the video right now, you can. However, if you want to see how I deduce the orbital velocity of a planet based on the gravitational force on it, keep watching. I'm going to make you do this in class anyway. So this is just in case you think, well, I'd rather see it done before I do it myself. But if you think, you know what, no, I want to try this on my own, please stop watching and we will do this in class. Okay. So if you decide to keep watching, this is for you. We know now that between any two planets there's going to be a force. Now this force, of course, points along the distance between the two planets and, of course, towards the other planet. So imagine that I have a planet here and another planet here. Now this one, of course, feels a force this way, and I'm going to assume that this one's so big that it barely moves. I'm just going to assume this just still. This one has a mass m, this one has a mass little m. Now this planet here, let's just say that for whatever reason it already had a certain speed that goes this way. So I'm going to show that with a blue arrow. So this is the velocity of the planet, and this is the centripetal, and this is the gravitational force. Now, remember that this is not a force. The only force that is present here is this. There's no other forces. So the net force here is the gravitational force. And then I ask myself, what sort of force is this? Well, it's a force that always points perpendicularly to my velocity. Because as this guy tries to move this way, this is going to force it to now move this way, but this is going to keep pointing towards the center of the Earth and perpendicularly to my velocity. Therefore, this is clearly a centripetal force, which means that my gravitational force is a centripetal force. And because it's a centripetal force, I can use this to figure out the speed of a body undergoing circular motion. Okay, so how do I do this? Well, pretty simple. I know that this is a centripetal force, so I can express this as an equation. The gravitational force is a centripetal force. Good. Now, I've done the physics. The rest is just mathematics. The gravitational force is this. G m over r squared. And that is a centripetal force. And remember that the centripetal force is mass times the centripetal acceleration, which is v squared over r. Okay? And now all I need to do is just solve for v if I know, for example, the distance of the planet to the other planet. Okay, well then m crosses out. This r crosses out with one of the r's. So I get v squared equals gm over r, and from here I get that v equals square root of gm over r. Being able to deduce this is required knowledge for the exam. But if you've been doing circular motion right and being very systematic on what is the net force, is it a centripetal force, and then just simply equating the net force with the centripetal force, this is extremely straightforward. That's it for today. I'll see you in class, and I will make you do this on your own, so make sure that you can do every single step in this process. See you later.